So in solid mechanics, when we're looking at the dynamics of a solid, if we have a little chunk of mass sitting here and it's attached on the end of a string to some fixed point here, then when gravity acts on it in this direction, it will swing down this way. If it starts out with an initial velocity of 0, then all it has at this location 1 is potential energy. When it gets down here to this location 2, it will have some kinetic energy and no more potential energy if we define this as our zero datum line. If when it gets to point 2 it runs into a spring, so that as it moves on to a point a little further over here, point 3, it's compressed that spring a little bit, it stores that kinetic energy back as potential energy into that spring. So if it was initially at height h, at location 1, it's not moving, so the velocity is equal to 0, but the potential energy is equal to mgh. At point 2, h is equal to 0, but now it's moving, and the kinetic energy is equal to 1/2 mv squared. And if there have been no losses along the way, no friction, nothing taking energy out of the system, it's a perfect pendulum in a vacuum, then the kinetic energy will be equal to the original potential energy. Then when we move to location 3, we've compressed the spring, we've done some additional work, we've got potential energy stored in the spring. And the details of that will depend on the spring constant and other factors. So similarly with a fluid, we can have potential energy due to elevation, kinetic energy due to motion, or potential energy as pressure, analogous to the potential energy stored in the spring. By pushing into the spring, you've stored some potential energy, or by pushing against a pressure, you've stored some potential energy. So if we have a fluid element sitting up here, we'll call this location 1. It's hardly moving. It's slowly, so that the kinetic energy is almost nothing, follows a path down here to location, which we'll call 3, where the pressure is higher, but the velocity is still small. And finally, it continues on through a nozzle to location 2, where the pressure is back down to atmospheric pressure, but the velocity is quite large. So if we were to draw some walls around this, we'd have to have a wall here converging into a nozzle, something like this. And if our little fluid element is initially sitting up on the surface of the water, it'll be at atmospheric pressure, so a pressure of 0 relative to the atmosphere. Down here it's at a higher pressure, and then it accelerates as it goes on out here through this nozzle and comes out at location 2 at this higher velocity, v2. So v3 approximately equal to 0, v1 approximately equal to 0. And again we have height h between the locations. So at location 1, not moving, v1 about equal to 0, potential energy equal to mgh, kinetic energy equal to 0. Pressure energy, the potential energy of pressure, equal to 0. At location 2, we have kinetic energy equal to mv squared over 2. Potential energy of pressure equal to 0, just like it was up at location 1. Potential energy of elevation equal to 0 because we're at the 0 height datum point here. At location 3, V3 was also about equal to 0, very close. Potential energy of elevation, 0 because we're at the 0 datum height. Kinetic energy equal to 0 because it's hardly moving. Potential energy of pressure equal to pressure times volume. That's the energy that went into pushing against the pressure as it went down there. Now, if there are no losses along the path followed from here down to here and out through the nozzle, there's no energy lost along the way, then the total energy in each of these cases must be the same.